Part 2 of section 2 of chapter 6. This is the last part of section 2 and also chapter 6. Following the MM1 queue in the previous part, here we have MMC queue. So here we assume that we have C servers. So the arrival process is based on Poisson process with the parameter lambda. The service times are based on exponential distribution with parameter mu, and we have multiple servers or exactly C servers in the system. So this is the state performance measures can be calculated by these equations. So here we have the row, the probability of having 0 customers in the system, the probability of having C or more than C customers in the system in long term, and for the L average number of customers in the system, W, WQ, LQ, and L minus LQ. Okay. Here we have an example for MMCQ, which is 6.13 from the textbook. So here we have the ticket counter at a movie theater. So the arrival of customers is based on Poisson process with 2 customers per minute, and the service time is based on exponential distribution with the mean of 40 seconds for the service time. Okay, so here lambda equals 2 per minute. So since the mean is 40 seconds, so mu will be 1 over 40, and since it's based on the seconds, we should multiply this by 60 in order to be in minutes. So it will be 3 divided by 2, or 1.5 customers per minute. Okay, so and here we assume that we have 2 servers. So here actually lambda equals 2, mu equals 1.5, and C equals 2, right? We have two customers, 2 servers. So rho will be lambda over C mu, so 2 divided by 2 times 1.5, or again 0.667. Okay, yeah. So we have the parameters here. We have the old parameters that we need to use the formulas in order to calculate the performance measures. So we go to the Excel file, to the sheet of MMC model, and then we will enter these parameters over there in order to have the performance measures. Okay. The next model that we have here is MMC and infinity Q. So here we have MM for arrival and service time, so exponential distribution for inter-arrival time, and exponential distribution for service time. And we have C servers here, and here we assume that the system has the limited capacity of N. So at most, N customers can be in the system at the same time, and the calling population is assumed to be infinite. So here, yeah, the only difference compared to the previous model is this: we have a limited capacity N, and we assume that N is greater than or equal to C, the number of servers. Okay, so N here is the system capacity. We call lambda over mu as A. We will use this A in the formulas, as you see here in P0 probability. So, and rho is lambda over C mu, and we know that lambda should be less than 1 in order to have a stable queuing model. Okay, so yeah, here we have again the formulas for calculating the measures. Since here, if we have N customers in the system, the next arrival cannot join the system because there is no room, right? So by this assumption, the effective arrival rate will be different than the arrival rate. So the effective arrival rate, let's show this by lambda E, and it will be less than lambda, right? And it will be calculated by this lambda times 1 minus Pn. So 1 minus Pn will be, I mean, yeah, 1 minus Pn will be the probability of having less than n customers in the system. So if we multiply that probability by the lambda, that will be the effective arrival rate. Okay, so yeah, WQ and W and L can be calculated by these formulas. And as you remember, in MM1Q, we had 1 minus P0 equal to rho, and this is just for the single server model. It's not actually valid in this model. Okay. Here we have an example for MMCNQ. Assume that a hairstyle shop again here. As you remember, the arrival was two customers per hour, and the mu is 3 customers per hour. So here we assume that we have just one server actually, yeah. And now we assume that this shop can hold only 3 customers, 1 in service and 2 waiting. So there's no room for more than 2 customers to wait in the queue. So this model should be, this model becomes MM1, 3, infinity, right? Yeah, MM mentions that the arrival is based on exponential distribution, service is based on exponential distribution, and we have one server, and the total capacity of the system is 3. Okay, so yeah, by having this model and having the parameters that we have here, lambda, mu, c, so we are ready to go for the formulas and calculate the performance measures. We do this in the Excel file in the sheet of MMCN queuing model. Okay, we can extend the previous model to be MMCKK. So here we have limited capacity in the system, and also the calling population is finite as well. Okay, so yeah, here you see that the P0 and Pn can be calculated by these formulas, and the performance measures L, LQ, lambda E, the effective arrival rate. You see how it can be calculated, and W is L divided by lambda E, not lambda, WQ, LQ divided by lambda E, and the rho is not lambda over C mu, it's lambda E over C mu. Okay, so let's have an example for MMCKK model. Here we assume that we have 2 workers, so this means the number of servers is 2, right? C equals 2, and we have 10 million machines. So here the number of machines actually mentions that the calling population is finite. So we have just 10 million machines that which 2 workers are responsible for these 10 machines. Okay, and the machines run on the average of 20 minutes, and then require an average of 5 minutes service period. Okay, so by having this, every 20 minutes we need to service the machines, right? So lambda equals 1 over 20, the rate of arrivals, the arrival rates for service, and the average 5 minutes, if we divide 1 by 5, that will be service rate, mu, right? So here we have lambda equals 1 over 20, mu equals 1 over 5, and then C equals 2, and then K for the system's capacity as 10, and also the calling population as 10 as well. Okay, so this model is MM21010 model. So by having the parameters, we go to the Excel file, to the sheet of MMCKK queuing model, and then we can easily enter these parameters over there and calculate the performance measures. Okay. So here we have the last model in this chapter, which is mg infinity. So the arrival is based on Poisson process with the parameter of lambda. The service time is based on a general distribution, but we know that the mean of the service time is 1 over mu, and its variance is sigma square, and system has infinite number of servers. Okay, so we have infinite number of servers. So yeah, by having these parameters, the performance measures for mg infinity queuing model can be calculated by these equations. Okay, so let's see here, WQ equals 0, LQ equals 0. Why? Because we have infinite number of servers, so we shouldn't have line here actually, right? The waiting time in queue will be 0, and there will be 0 customers in line in the queue in the long term. Okay, and the P0 will be calculated by this equation. So you can refer to the textbook for an example for this model as 6.15. Okay. The models that we had so far are simple and standard queuing models, but in the real world, we may have a network like this example, and as you see here, they are complex, right? So in this example, let's say the arrival rate to this to this machine, I mean the first queue actually is lambda, and if we assume that the service rate is mu for the machine 1, then this service rate will be the arrival rate for the second queue, right? So yeah, by doing this, we can somehow analyze mathematically the network queuing models, but usually for these kind of complex systems, it's better to go for simulation instead of doing mathematical analysis. Okay. In summary, in this chapter, we had queuing models for simple and standard models, and you saw that how we can calculate the performance measures by having the system's parameters like the arrival rate, service rate, number of servers, and so on. Okay. These standard and simple queuing models are based on some assumptions, right? So usually we don't have these assumptions in the real world, so but we can use actually this simplified models with the certain assumptions in order to obtain approximations about the actual system, and we can use the approximated actually values obtained by these queuing models to verify and validate the simulation model. And also we can use these models even with the simplified assumptions to obtain some measures that are hard even by simulation to obtain. For example, the number of servers, right? If you want to obtain the number of the best number of servers with simulation, you need to try different numbers for the servers, and it takes time, right? But by having the queuing models, you can assume that those assumptions are valid for the actual system, and then you may obtain the approximated number of servers very easily in a very short time. Okay, and the performance measures that we have in this chapter are just for the steady state behavior, but if we build a simulation model, we can obtain the performance measures for the transient behavior as well. Okay, so yeah, this is chapter 6, and you can read chapter 6 of the textbook as your reference. Okay, thank you.